Hello class, this is Professor Finan. Today's lecture, we're doing lecture 2 of the Regression for Scientists and Engineers course. And so today's lecture 2.1 is just some probability and statistics concepts that we will use later on in the course. So let's get started. Mean and expectation value. And so when we collect data which we will use in our regression model, we have a finite population. Basically, our data represents a finite population. And so generally when we collect data, we might have our independent variables x1, x2, xn for our n observations. And so we should calculate the mean of our sampled x data. And so the mean or the expectation value is simply x bar equals, it's just a simple arithmetic mean. The summation from I equals n, and remember n is our number of data points of each individual xi, then divide by 1 over n. And that's equal to mu, or our expectation value of x. And so that should be a review for everyone. And so the next concept is variance. And so the variance of x quantifies how the data fluctuates about the mean, and the mean of the predictor. And so the variance formula, and this is for a population. So the population variance it's usually the sigma squared. Here I'm using subscript x because we're doing it for the predictor or the independent variable. And so it's 1 over n times the summation from I equals 1 to n of xi, that's the individual data point, minus the mean value, and that's squared. And we call this term xi minus x bar, we call that a residual. So it's the difference or the delta between the sampled data point and the mean of all of the sampled predictors. We call that a residual. And then the standard deviation is just the square root of the variance. And so we usually use the symbol sigma for the standard deviation. Okay, now this is the first important concept. So this should have been, the previous 2 slides should have been reviewed. So population versus sample mean and variance. And so in many applications, we do not have access to the entire population. And so our data set is limited to a subset of the population. We call this a sample. And so we must make inferences about the population using the incomplete sample of the population data. And this is what we can use the regression model to make inferences. And so for example, I'm a professor at UNIS, so a population is all of the graduate students enrolled at UNIS. And now I teach a course called NE 559, and there's about 20 graduate students in that course this semester. So a sample of the UNIS graduate school population would be the 20 students that are currently taking my course. And so the population contains, it's the complete data set. A sample is a subset. And so a sample is a subset drawn from a population, and hopefully the sample will be representative of the entire population for the information we want. And so for example, let's go back to this graduate student example. What is the average age and variance of the graduate students enrolled at UNIS? And so I could survey the students in my class, and we could use the 20 student sample from my course to estimate the population mean and variance. But we should think, how might the average age and variance be different or similar to the graduate student population enrolled at a science and engineering university in the United States? So let's just take a quick, minute or two, let's think about this. First is we're going to calculate the class average age, and that's from my current class. I have 20 graduate students, and it's a nuclear engineering course. But we have, it's a course on regression. So there are students from other departments that's taking it as well. And so let's think, comparing what type of bias or biases might be introduced when you use the NE 559 class example. So of the students, of the 20 students, about 16 are nuclear engineering students. We probably have about, and this is biases relative to the graduate student population at UNIST. There's probably about 7 or 8 international students. I think there are 3 female students, 17 male students. And so when you have a subset, you should look at the individual characteristics. How well is that subset representative of the whole population? So UNIST, the graduate student population, there are, I don't know the percentage, but there's probably a large minority of students are international students. And so I do have, I think we have at least three countries. We have about, I think 7 or 8 international students currently in my course from, I think, at least three countries. And so what could be some possible biases from a subset versus the whole population? One thing is, for example, male-female. So we have 3 out of 20, so about what, 15% of the students are female students, and I don't know what is the total percentage of female students at UNIST. And also let's go on to the third point. What differences might you expect between the UNIST graduate student population and a graduate student population from a similar sized science and engineering university in the USA? And so one major difference is, think about especially Korean students who are male. In Korea, they have the mandatory military service, usually for 2 years. And so one possible bias is, what percentage of these populations are Korean male students who served in the military? Because a lot of the male graduate students, they might be on average 2 years older. And I encountered that when I first came to Korea in 2014, or when I came back to Korea in 2014. When I joined my first company, there were about 4 other new PhD graduates, male Korean students. They were all about 2 years older than me. All 4 had done their military service. So that's one, for the USA example, that's definitely because of the mandatory military service in Korea, there might be a bias from the one population to another. And so how all of those different, the percentage of international students, the male versus female ratio, of the male Korean students, how many did military service, and is that representative of the entire graduate student population? And so when you start to collect data for your study, you need to keep your mind open and start to think about what are the different biases, is there a bias or any biases in the sample that you're collecting. So these are just some brainstorming examples. Okay, and so once we've collected data that's a sample, we can also calculate the sample mean. And so it's the same formula as the population mean. And generally, the sample mean is an unbiased estimate of the population mean. But the formula for the sample variance is a little bit different. And to be an unbiased estimator, we actually have to correct the standard deviation or the variance formula using 1 divided by n minus 1 times the residual squared. And this is because if you sum up the residuals sum to 0, so there are n minus 1 degrees of freedom. And basically what this is saying is, we use the data points xi to calculate x bar. And so it's almost like a double accounting. We're using the variable xi is showing up 2 times in the same equation. And so the sample means are not independent of the data points. And the reason why I'm actually writing out these equations is because when you use software, whether it's Microsoft Excel or built-in functions in MATLAB and Python, they'll say it's the standard deviation formula or the variance formula. Most of the time you actually don't know, are they using the sample variance formula or the population variance formula? And so you need to determine that yourself, and you should actually program these equations yourself. Because actually for some linear regression models, for example, the simple linear model, we can directly use these means and variances. So even though I know many of the softwares have built-in functions, you don't always know exactly what they're calculating unless you look into the source code or look into the documentation. I recommend you always it's one line of code, program it yourself so you know exactly which one you're calculating. And so it's always better to program it yourself. Because the more you personally work with your data set, the more familiar you will become with it. Okay, and so here's a little bit of a pro tip from my experience with building regression models. So after you've collected the data, the very first thing you do before doing really anything else, before you start building the regression models, the first thing you do is you should calculate the means and the variances of all of the independent and dependent variables. And so the formulas are the same. So before I was showing it the mean and variance for the one predictor variable. You can do that for the dependent variables, and if you have multiple predictors, you should calculate all of the means and the variances. And here I'm using the population variance. I'm assuming it's a complete population. And then after you do that, look at, on a percentage basis or a relative basis, what is the standard deviation relative to the mean? Okay, and let's go back. Let's say our y is a temperature measurement, an atmospheric and environmental temperature measurement. And so in the one example, we did it from, I think, 20 degrees Fahrenheit up to almost 95 degrees Fahrenheit. And so you should calculate what is the mean, and then what is the variance. And then see what is that on a percentage basis. Is there a 5% variation in your observed output data, or is there a 50% variation, a factor of 2 variation? So if this percentage is large, there's probably a strong correlation between the explanatory variable, so the x, and the response, the y variable. Or there could just be a very large random noise. That's another possibility. And so if the standard deviations are large from this population or sample statistics, you know there's probably some sort of underlying relationship that we need to find. And also a small variance in the x space. So in one of the independent variable dimensions, a small variance might indicate a too narrow range of x was sampled to adequately determine the relationship and the correlation. Okay? And so generally we want our regression model to be predictive over a range of x values, the whole range of our application. But if our data set is only sampled a narrow range, that can lead to problems. And also the small variance in the output variable might indicate no relationship, and the variation in y might just be the random noise. Or if there's a large variance, that also could be large random noise. And so the point is, this is the sample and population statistics. This is the zeroth order information. And so this will help you familiarize yourself with your data set and gain physical insight into the problem, into your data, and the orders of magnitude of what we're dealing with. Like I said, you should have, what are the orders of magnitude? Are we talking about 5% variation, or are we talking about 50% variations? Okay, another related topic is called weighted mean and variance. And so there's a subset of parametric and nonlinear linear and nonlinear parametric models are what are called weighted linear least squares and weighted nonlinear least squares. And there, instead of using the arithmetic mean and variance, we use weights. And so there are several reasons why you might want to do this. You can control the magnitude of the residuals if the dependent variable varies significantly over the range of x. Let me give you an example. This is the residual, okay? This is yi minus y bar. If the yi's vary by many orders of like let's say from 1 to 1,000, y bar might be, it's maybe probably somewhere in the middle, but the magnitude of the residual, it basically becomes biased towards the larger numbers. And so if you have a wide range, by using weights, you can control the magnitude of the residuals if this dependent variable varies significantly over the range of x. And also sometimes when we do measurements, the random noise magnitude might not be constant over the input space. So for example, let's say in electrical circuits, you have some sort of measuring device that has an electrical circuit and you have an amplifier. So you're taking in an electrical signal and then amplifying it. And so or maybe if the signal is proportional to what you're measuring, the noise from your base signal might then also be amplified. And so in some measurements, the random noise is not constant in the input space. You can use weights to also then to control the influence of the random noise. But the one thing to remember is the weights, which I'm going to use the letter W. These are subjective and have to be, you have to choose those, as the analyst has to choose those weights. And so the weighted mean formula, it's similar to the population mean. So the x bar is 1 over then the summation of the weights times the summation of the weight I times data point xi. And then y bar, same. And usually you will normalize the weights. The sum of the weights should equal 1. You actually don't have to do that, but generally it's good practice to have those the weights be normalized. So actually sometimes you will actually omit that denominator term if you assume that it's normalized. For the variance, this is where it gets a little bit tricky and application specific. There are different formulations and corrections to the variance formula for the weighted variance, but generally you can use just the corollary to the population variance formula. So this is whether it's biased or unbiased, but you're already when you introduce weights, subjective weights into your problem, you're introducing bias relative to the true population statistics. So this is where it's not quite as important as the variance, the exact form of the variance that you use. Okay, that is it. So those should be some review, but remember the first thing you do is you calculate the mean and variance of both the predictors and also the output variable y. And that's your 0th order information that will help you give you insight into the problem.